Hello everyone, my name is Aidan Ziegler and today I'll be talking to you about a sensing system for low-cost condition monitoring of remote assets developed at the University of Western Australia's System Health Lab. Firstly, a little background on the motivation for this project. Australia is an exceedingly sparsely populated country, having only 3.2 people per square kilometre on average. This, coupled with an economy that relies heavily on agriculture and mining, results in a large number of remote assets, such as road signs, power lines, switchgear, windmills, pumping stations, and much more. The condition of these assets can be difficult to monitor due to their remoteness and often involves sending personnel to visually inspect assets, a costly process when said assets are far apart and may not be easily accessible. So from the motivation, we can form a set of requirements for a device that can help provide information about these remote assets. The device that is the focus of this presentation aims to address one aspect of remote condition monitoring: unwanted vibration events. Unwanted vibration events can occur due to a multitude of factors, such as high winds, being impacted by a vehicle, or an unbalanced rotor. Given that the device will be used to monitor remote assets, there is no guarantee of support infrastructure. Hence, the device needs to be fully self-sufficient. Due to the sheer quantity of remote assets and the harsh nature of the Australian environment, the device should be semi-disposable and hence is required to be inexpensive to manufacture. For this proof of concept, we're targeting a cost of less than $100 AED. Transporting highly skilled labour to a remote asset can be an expensive process. Hence, the device should be able to be installed with absolute minimal training. In order to provide the end user with a benefit, the device must provide information about the condition of the asset for an interval longer than the visual inspection period. This means that the device requires a long operational life, and we're targeting greater than 1 year. Finally, the platform should be easily accessible to customize the device to the exact requirements needed by the application. So this brings us to RAMI, the Remote Asset Management Indicator. We were heavily focused on making a system that is easily accessible to developers with absolute minimum onboarding time. This heavily influenced the component selection. All components are accessible through the Arduino IDE using open source libraries. The ATmega 328P microcontroller forms the basis of the RAMI device, and you may recognize it from the extremely popular Arduino series of development boards. It also provides a highly configurable power environment, allowing for individual components to be switched off when not in use, making it an excellent candidate for this proof of concept board. The DSM3231 RTC module allows for alarms to be set periodically to wake the microcontroller. The RFM95W is a LoRa module that allows for long-range communication. And the ADXL345 accelerometer is a 3-axis accelerometer with great open source support due to it being available as a SparkFun module. As the system is designed to run in a small power supply window, powered by a lithium cell and having an operating voltage of 3.3 volts, a low dropout linear regulator is used for power conditioning. So on this slide, we see the schematic for the RAMI device. The device itself can be built very simply, consisting of 20 discrete components in its most verbose implementation. This verbose implementation includes an external clock for the ATmega 328P and a serial breakout to assist with development. At its simplest implementation, the device only uses 13 components, providing only the minimum functionality required to monitor an asset. And here we see the final device. The device itself is hand soldered. There's no specialist equipment required to manufacture. This creates a low barrier of entry for anyone looking to use the project. Wide traces on the PCBs allow for low fidelity manufacturing. The parts for the device are easily sourced from any major electronics distributor, and we have it shown to the right in a 3D printed case. At 3.3 volts, the device is designed to be powered using a single lithium cell or multiple in parallel, as shown on the right. So there are three power states accessible from the electronics: sleep, monitor, and transmit. In order to test the device's performance in each of these areas, Arduino sketches were created that put the device into one of the states and holds it there. These test scripts are available on the System Health Lab GitHub. Electrical characteristics measurement and testing setup was performed through Jupyter Labs using the VXI11 package to communicate with a Siglent multimeter. Transmission is by far the most expensive process, and at a low data rate can last for a few seconds. Hence, we wish to avoid this state unless absolutely necessary. The accelerometer is capable of streaming data into the device at rates measured in the hundreds of hertz. Transmitting all of this data over a low bandwidth connection is impossible. Hence, the device needs to sift through this data in a way to provide meaningful information back to a data aggregation service. To provide meaningful data about the types of forces experienced by a remote asset, we monitor the asset for a set period of time, then send back the peak force experienced. This gives the end user an idea of the magnitude of forces experienced and can be used to infer if an asset should be inspected or not. This allows for asset inspection to be event-driven rather than schedule-driven. Other aggregation methods can be used, such as RMS, averaging, or median. So when the device is experiencing a vibration event, if the magnitude of the vibration does not change, then there is no reason to send the same value back to the aggregator continuously. Take the signal shown on the right, where a sudden increase in vibration amplitude is measured. When there is activity, we monitor the amplitude at a polling rate, shown by the yellow dots. We can then draw a threshold around the signal that is smaller than the region of interest, indicated by the red lines. When the value changes by more than the threshold, it sends the data back to the data aggregator. Transmissions are shown by the red dots. The data aggregator can then use the threshold and what it knows about the monitoring period to reconstruct the signal, shown by the purple line. This system can be tuned to optimize data fidelity and battery life. So two states handle the data collection and heartbeat signals. The active state can wait for a monitoring period, or if the accelerometer registers a configurable period of inactivity. If the active state has been woken by an inactivity interrupt, it'll set the state to inactive, set a still alive alarm, and return to sleep. Else, if the active state is woken by a monitoring period alarm, it'll start collecting values, performing the edge processing mentioned on the previous slides, set an alarm for the next monitoring period, and then return to sleep. In the inactive state, we first check if we were woken due to accelerometer activity. If we were, then we set the state to active and continue in the active state. Else, if we were woken to send a heartbeat signal, we transmit the heartbeat, set a new alarm for the heartbeat signal, and return to sleep. The overall implementation exists as an Arduino sketch using the Pro Micro device definitions and takes less than 400 lines of code. Communication is achieved through a custom binary structure that packs data into 7 bytes. The first byte function provides a purpose for the transmission, be it data, heartbeat, or inactive signals. The second byte provides a unique identifier for the device. The third byte is a nonce incremented each packet to catch packet loss on the data aggregator side. And data is a uint32, representing the magnitude of the experienced force. Some configurable overhead is added by the RFM95W. A header containing information about the packet and a CRC is appended to the end. So 2 range trials were carried out. A TTGO LoRa module was used with a simple Python driver to communicate and decode messages for the range trials. A trial was considered successful if it could transmit 20 packets of 20 bytes in a row without fault. The short range trial was a worst case scenario: noisy environment, obstructed view, and low transmission power. The long-range trial was the opposite: line of sight with a lower data rate, a higher spreading factor, and a greater transmission power. The short-range trial achieved 379 metres, and the long-range trial achieved 3.05 kilometres. The final cost of the device is $63.02 Australian. This equates to a little under £35 depending on the exchange rate. The parts required to manufacture the device can be easily sourced in small quantities from large electronics distributors. The prices shown come from DigiKey and make the assumption that we are purchasing the minimum quantity. The price goes down significantly under bulk purchase agreements. It only requires a soldering iron to assemble and hence does not require an expensive setup to manufacture. And some typical competitors are shown on the right. The Slamstick C is a high-resolution logging device, providing more insightful data but over a short period of time to local storage. The Beanair Willow is a similar product that adds wireless functionality as well as data logging. And finally, the device that is closest in the space is the radio bridge activity sensor that will send a signal over a LoRaWAN network when activity is detected. However, only provides information about a single threshold, not a dynamic signal. This is a very fast-moving field, and whilst devices are being made to replace existing condition monitoring units, this project is about moving towards event-driven monitoring for assets that are usually monitored infrequently, if at all. For this to occur, we need to be able to monitor assets at scale, and this is what RAMI aims to achieve. Currently, the device is at Technology Readiness Level 4. There are a number of improvements to be made before the system is ready for real-world use. Foremost being data security. Presently, at the proof of concept stage, no data security has been included. This leaves the device open to a multitude of attacks, such as spoofing and interception. Secondly, we can improve power management. We are currently using a linear regulator for board simplicity. However, the system could utilise a buck-boost converter for higher efficiencies. This would also allow a much greater voltage input window. The chipset could be improved, as we chose the ATmega 328P due to its great open source support. However, lower power consumption chipsets exist that also integrate the RTC module. This is more power and cost efficient whilst reducing board complexity. It would require libraries to build mostly from the ground up to support the device though. We can shift to using protobuf messages instead of a custom binary structure. This would codify a standard for message transmission and make unpacking data in any language trivial. We also have the option to re-specify the accelerometer. Once again, this was chosen for its open source support. However, we are only utilising a fraction of its potential. Cost and power efficiencies can be made by specifying an alternate accelerometer. We can also modify the board to include layouts for other sensor types. This will allow condition monitoring of items such as tanks, structural supports, and solar exposure. The range that is possible with LoRa is much greater than we achieved in a long-range test. Hence, a number of improvements can be made to the antenna and the gateway in order to get the most range out of the device. Finally, there needs to be development of the back-end aggregation platform in order to provide support for these additional improvements and to provide a meaningful method of using the aggregated data. So these are some of the open source libraries used. In order to make them compatible with the RAMI device, some modifications had to be made to both the LoRa and accelerometer libraries. Forks of these libraries, along with all the documentation for the rest of the project, are available on the System Health Lab GitLab page, pictured above. So that brings us to the questions section of this presentation. Thank you for listening, and let us know if you have any questions.